Thank you. Oh, here we are. Thanks, Katerina. I had the pleasure of working with Katerina. She came to Michigan. We did a paper together, so it's nice to see her again. And it's a great pleasure, an honor to be giving this talk. So I'm going to talk about Bayes and argue that it might be a good way to think about a framework for dealing with official statistics in the coming years. So here's an overview of what I'm going to talk about. I mean, I'll talk a little bit about design-based versus model-based survey inference, a well-developed topic for the statisticians in the audience, I suspect. And then what I view as the sort of current orthodoxy for how statistics are used in official statistics, which I call a design-model compromise, and talk a little bit about strengths and drawbacks of this current orthodoxy, and argue sort of along the lines of the first session a little bit. I changed the slides, having heard Dr. Rademacher's talk a little bit to try and fit in with what he was saying. But so I'm going to argue that sort of multi-source official statistics, big data, that kind of stuff, really needs a new inferential architecture. And I'm going to argue that Bayes, and particularly calibrated Bayes, is a good architecture. I have a couple of applications that I'll outline to you at the end they're actually somewhat related, as you'll see. These come from the time when I was at the census, so I do want to make the usual disclaimer that these are the views of me and not the views of the Census Bureau, U.S. Census Bureau. So, design-based versus model-based inference. So the classical approach to inference from a probability survey is design-based inference. And the key idea is that population values in this way of doing statistics are treated as fixed. And the statistical inference is based on the probability distribution determined by the sample selection. Obviously, this assumes that we have a probability sample, or if we don't have a probability sample, we pretend as if we had a probability sample. We might call that quasi-randomization. Model-based inference is the survey variables are assumed to come from a statistical model. The probability sampling is not the basis of inference, but is still very useful for making the sample selection ignorable in a sense that is discussed quite nicely in the book by Bayesian book by Gelman et al. 2003. I think probably the original idea comes from Rubin's work in the 1970s. There are two main variants of model-based inference. Superpopulation modeling is probably those of you who work in this area more familiar with. Frequentist inference based on repeated samples from a superpopulation model. I view this as a little bit of a hybrid between frequentist versus modeling, versus Bayes, if you like. And then Bayes, which is to go the whole way, put a prior distribution on parameters in the model and base inference on finite population quantities or parameters on posterior distributions. And it's kind of a fascinating part. This design-based versus model-based inference has been an interesting debate over the years in survey sampling. And it's really a fascinating part of the more general debate about frequentist versus Bayes inference in statistics at large, with the design-based approach being primarily very pure form of frequentist inference, the Bayes being, in a sense, a pure form of the model-based inference. Just, Danny put some equations up this morning, so that's allowed me to put a little bit of notation, but I'm not going to dwell too much on the technical details here, but just in brief, some notation. You have a population of size capital N. You have survey variables that could be a vector, y1 up to yn, the values for each of the values in the population. We have design variables, which I'm calling z here. And then there's a finite population quantity. I'm focusing mainly on the finite population part here, q, which is some function of those things, which is what you're trying to estimate, let's say a mean or a total or something like that. I'm sorry about this, the squiggly thing here. That's a font problem, as you probably noticed. That should be a big sigma. It's the only one that's in the talk, so I didn't think it was worth fiddling with. So, anyway, we have inclusion indicators that indicate which cases are in the sample, which cases are not in the sample. And that's treated as a random variable in the design-based approach. And then you have the included part of Y, the part you actually get to see in the survey. Then you have an estimate of Q based on the data you see, which is the included part of Y, Y inc, I, and Z. And then you have some estimate of the variance of an estimate of the variance of the true variance of Q hat. And then you calculate a large sample confidence interval. For a 95% interval, you might take the estimate plus or minus 1.96 times the standard error, familiar for one single courses in statistics. How do we choose this estimate? Well, that's an interesting question. In the design-based approach, you seek it to have good design-based properties like design unbiasedness, which says in repeated sampling the estimate averages out to the true value of Q. That's really too strong a condition in practice. Or something weaker like design consistency, which says that as the sample size grows, the estimate tends to the true population quantity. It would be nice from a statistical point of view to seek an estimate that's in some senses efficient or design efficient. However, if you just fix the population values in the inference, which is what we're doing in design-based stuff, then you can't really achieve optimality without having a model. So there are many ways of, in some senses, I think design consistency is too weak and design unbiasedness is too strong. So how do we get these estimates? Well, there are usually implicit models underlying these estimates. So a regression estimator, there's an implied regression model underlying it in the background, or a ratio estimator, there's a ratio model. So there are models sort of lying around in the background here to motivate the estimator, but they're not the basis for the inference. What are the limitations of the design-based approach? Well, the first one is kind of obvious. Since we're assuming we have a probability sample, we have to have a probability sample. But true probability samples, of course, harder and harder to come by these days. So we really have to pretend quite a bit in order to do design-based inference. So non-contact, non-response is increasing. Face-to-face interviews are increasingly expensive. If you really want to combine data from a survey with data from other sources, as in the sort of the big data conversation, then you really can't do that from a design-based perspective. So you do need a different paradigm. In fact, you really have to model. Another limitation from my point of view is that the design-based approach is essentially an asymptotic approach. It assumes you have large samples, which means that if you're interested in small area estimation or any situation where you have very small samples, then it doesn't work very well. So this is my little sketch of the fact that design-based methods live in what I call the land of asymptosia. So the land of asymptosia has sun and you're above the clouds and everything is great. The sample size is large enough. But if you're in the murky subasymptotial forests, like if you're doing small area estimation, then it doesn't really work very well. So what's the alternative? Well, there's a model-based approach, or model-dependent, sometimes known, where you actually have a statistical model for the survey variables. These models are really the basis for the inference, the estimator, the standard error, and interval estimates. And as I said, the two main variants of this are superpopulation modeling and Bayesian or full probability modeling. But they have a common theme, which is prediction. So essentially, the common theme is to infer or predict about non-sampled or non-responding parts of the population, conditional on the sample and the model. Well, I'm arguing for Bayes. So superpopulation models are super, but Bayes is better. Why is it better? Well, I'll try and convince you a little bit later, but a quick answer is if you have small samples, then I think Bayes does a better job from a frequentist perspective. And And I noticed that I did a little survey yesterday. I was jet lagged, so I probably got the data wrong. But I looked through the booklet of talks. There are about 180 talks in the conference, and there's a talk by Van Tongeren in the quick dating session as the only one that actually had Bayes in the title, apart from this talk. So it's actually interesting that Bayes, which has become very pervasive in other areas of statistics and science, very highly cited, a lot of the highly cited statisticians are Bayesians these days. It's extraordinarily striking to me how in official statistics it's hardly used at all. And I'd like to try and at least push you a little bit in the Bayesian direction. So I tried to do that when I was at the Bureau, so you can talk to the Census Bureau people to see if I had any success there. So. Well, it's more notation, so I'm not going to go through the technical details. After a glass of wine at lunchtime, I basically just want to fall asleep. So if you can fall asleep through these equations if you don't like them very much. But the basic idea of Bayes for surveys is you have a model for P of y given z. It's actually really just a prior distribution for y. Then you have data y inc, and you calculate the posterior distribution about the thing you're interested in, conditional on the data y inc and z. So it's based on the posterior predictive distribution. So you could summarize it, for example, by an estimate be like the posterior mean. A standard error would be something like the posterior standard deviation. A 95% posterior probability or credibility interval plays sort of the similar role to the confidence interval, but it has a more straightforward interpretation. Usually we specify this prior distribution through a parametric model. So P of y given z is expressed as P of y given z and theta, averaging over theta, where theta is a parameter. So P of y given z and theta is then a parametric model, which is sort of essentially the same as the superpopulation modeling approach. But then you're adding a prior distribution to theta. That's the thing that differentiates Bayes from superpopulation modeling. You can then make inference about theta based on its posterior distribution computed by Bayes' theorem. That is, the posterior is the prior times the likelihood. So that's my 2-minute spiel on Bayes. So what's the difference between a design-based versus modeling perspective? Well, I like to use this example of PPS, probability proportional to size sampling. Z here is a size or a weight variable. Y is the survey outcome. And we're selecting the sample with probability proportional to size. So the pi I, the selection probability, is proportional to the value of Z. The usual estimator for PPS sampling is a Horvitz-Thompson estimator, where you divide the y's in the sample by the probability of being selected, and then sum and divide by n. Well, from a modeling approach, you're not going to use these sizes or weights as weights for the sample cases. I view the z's as more a covariate, and so the goal, if you look at my little picture on the right here, you'll see z is observed for the whole population, z and y is observed for the sample. The goal is really just to predict the values of y for the non-sample cases, and z, the size variable, essentially becomes a covariate. And the prediction approach, or the modeling approach, is to predict the non-sample cases. And if you do that using the model, actually maybe I can try and use the mouse here. So this model here, you see my little arrow here, this normal model, y is normal with a mean beta pi I and variance sigma squared pi I squared, leads to the Horvitz-Thompson estimator as a prediction estimator for that model. So you might want to make this more robust. So what I did in a paper with Hui Zhang was replace this fairly structured model with a spline model on the probability of being selected. So you build a spline regression, and then also allow the variance to depend on pi I raised to the power of k. So I'm sort of making the model a bigger, a more flexible model. So this sort of illustrates the approach, and then simulations in this paper you can see that when the Horvitz-Thompson model kind of applies, then this more general model does a little bit worse, but not much worse than the Horvitz-Thompson estimator. But if the Horvitz-Thompson model doesn't apply, then this more flexible model does much better, both in terms of root mean squared error and in terms of confidence coverage. So not only improving the efficiency, but also improving the frequentist properties. Perhaps some of you may be familiar with the most extreme deviation, comic deviation from this Horvitz-Thompson model was the Basu elephants example, that some of you may be familiar with. It's a famous example in theory. Okay, so that's a little bit on models. So why do I like the model-based perspective? Well, it's a flexible and unified approach for all survey problems. So it deals with issues of non-response, response, and matching error, small area models, combining data across sources, and big data, I would argue. The models might be complicated, but essentially this is the right underlying perspective. Somebody mentioned causal inference this morning from official statistics, and that also requires models to do a good job. Why do I like Bayes? Well, it's not an asymptotic approach and really gives you better small sample inferences. And I've done a lot of simulations over the years to show that putting a flat prior and doing Bayes gives you better frequentist answers than, say, assuming maximum likelihood and assuming large samples. Probability samples are still very important, though. It's justified because it makes the sampling mechanism ignorable, and this is very important for giving you robust inferences. Rubin's theory, this is Don Rubin's theory in the 70s, on ignorable selection and non-response, is to my mind the right way, the right framework for assessing the idea of non-probability sampling. Non-probability sampling is a special case of ignorable, but the more general way of viewing it, which encompasses non-probability samples, is to use Rubin's theory. Another reason I like models is it brings survey inference closer to what I view as the statistical mainstream, in a sense that most other areas of statistics actually use models. So the lady on the right, sometimes I switch the faces around because I don't want to offend anybody here, but the lady on the right is an economist who's sitting somewhere in the official statistics agency, and she's used to fitting econometric models. And then this design-based guy comes around and says that we have to apply these design-based statistical standards, and they basically talk across each other because they're really thinking of very different paradigms. My view is that if you bring it all within the modeling paradigm, then people are not talking past each other anymore. So the gentleman in the back is the Bayes frequentist gorilla in the room. So. Well, what's bad about models? Explicit dependence on the choice of model, which has subjective elements, is clearly viewed as a negative. Although you could argue that the assumptions of models are more explicit, and so you can actually evaluate them. Perhaps the worst thing is that if you have a lousy model, you get a lousy answer. So bad models provide bad answers. And so there's justifiable concerns, I think, about the effects of model misspecification. Models are needed for all survey variables, and so it potentially could be more work than just churning out weighted estimates. So what's the current orthodoxy? Well, I call it a design model compromise, essentially because for large samples and descriptive statistics, we like to be design-based, perhaps with model assistance, so model-assisted estimators like regression calibration is still within the design-based paradigm, but is using models to improve the estimate. But then for other things, we use models. So for small area estimation, we basically do modeling. Non-response, you really have to do model time series is one area where we do a lot of modeling. So what's good about this? Well, it's attempting to capitalize on the strengths and weaknesses of both the paradigms. So from a pragmatic point of view, I can see that it's reasonable. On the other hand, I think it entails a certain degree of what I call inferential schizophrenia. And I have a little illustration of that in the next slide. So here we have, if you're going to be model-based for small samples, and you're going to be design-based for large samples, so there's my n-omometer on the side, which is the sample size thing, then somewhere in between you switch from design-based model inference into model-based inference. So I call this the point of inferential schizophrenia, because I'm not sure whether I'm doing a model or a design at that point. So how do I choose this point of inferential schizophrenia? And should my entire statistical philosophy and inference be different when n is below that line and when n is above that line? So if n is 34, I'm going to be model-based. If n is 36, I'm going to be design-based. So it's a little bit of a nonsense, I think, from a coherent point of view. In fact, the confidence interval for n equals 36 is actually going to be wider than the confidence interval for n equals 34, because you're using the model, which is going to increase the precision for the lower sample size. So that's not very consistent either, since you kind of expect the interval to get wider as you get less data. The Bayesian or hierarchical Bayes sort of model for this kind of a small area thing is much more coherent to my mind. So here's the sample size increasing with n, and you know, the usual hierarchical model estimate is essentially a weighted combination of the direct estimate from the, if you like, the design-based estimate, and a prediction from a model, that's mu sub I, and you weight them differentially, where the weight given to the model increases as the sample size goes down. So as you have less and less information, you borrow strength more from other areas. So Bayes multi-level modeling borrows strength increasingly from the model as the sample size decreases. Okay, so now I'm going to talk about what calibrated Bayes is and why I think it's a good form for thinking about how to do official statistics. And so what is calibrated Bayes? Well, essentially it argues the position that the frequentist should be Bayesian, essentially that the inference for a particular data set should be based on Bayes, posterior distributions. Essentially, and I think there are lots of reasons for this, which I'm not going to go into here. From a theoretical point of view, under a correctly specified model, which is a very big caveat, Bayes is sort of the right thing to do. On the other hand, Bayesians need to be frequentist because we never have the right model. So all models are wrong. Some models are useful, as Box said. And if you have a lousy model, you can get a lousy answer. So you have to be very careful about the model that you base this Bayesian inference on. And inferences should be robust to misspecification and have good repeated sampling characteristics. So calibrated Bayes, essentially inference is based on a Bayesian model, but the model that is chosen to yield inferences that are well calibrated in a frequentist sense. So you aim to have good frequency properties. In particular, posterior credibility or posterior probability intervals have approximately the nominal frequentist coverage. A couple of quotes I like. George Box, who died last year, a very wonderful English statistician, in a key paper in 1980 said that I believe that sampling theory is needed for exploration and ultimate criticism of the entertained model in the light of the current data, while Bayes theory is needed for estimation of parameters conditional on adequacy of the model. So very much breaking it down into two parts. The criticism or checking of the model being based on frequentist ideas, but the estimation, or I would say more generally, the inference coming from by applying Bayes. The other paper I really like on this area is a paper by Don Rubin, and this is a quote from his Annals paper. The applied statistician should be Bayesian in principle, but calibrated to the real world in practice. Appropriate frequency calculations help to define the tie. Frequency calculations are useful for making Bayesian statements scientific in a sense of capable of being shown wrong by empirical test. Here the technique is the calibration of the Bayesian probabilities to the frequency of actual events. So calibrated essentially means I want to have good frequency properties. I want to have my cake and eat it. What does that mean for surveys? Well, it does mean, I think, that this calibrated part, having good frequency properties, requires that models incorporate, have good repeated sampling properties, and that means, in general, weak priors, so what might be known as objective Bayes, and also models that incorporate sample design features. So you can't just ignore the design weights, or you can't ignore clustering if you have multi-stage sampling. You have to incorporate these design features into the model in order to get good inferences. So how much time do I have? 5 minutes? Yeah. So a couple of census applications. And these are, one was an analysis I did with colleagues at the Bureau, Census Bureau on Voting Rights Act, special tabulation, and the other is American Community Survey and what I call the standard error, which I think is a common thing in official statistics. Since I've only got 5 minutes, I'll skip over, well, I can probably do this fairly quickly. So the Voting Rights Act, so Section 203 of the Voting Rights Act has this thing where you have to determine counties and townships in the United States that are required to provide language assistance at the polls. And the key provision of this deciding which of these counties and townships are subject to it is whether there are more than 5% of voting-age citizens of political district are members of a single language minority and are limited English proficient, or LEP, as is the lingo. So there's a 5% cutoff. If you're above the 5%, and there's some other things you have to do, but this is the one, actually the main one, then you have to have this special assistance, language assistance at the polls. Previously, the Census Bureau is charged with figuring out which districts they are. It's actually quite politically charged, because anything to do with elections in the states, as in other places, is very politically charged. Previously used direct estimates from the long form and decennial census data. So now what they're left with the long form being gone, is the American Community Survey and 2010 census data. And the requirement was to produce estimates in fall of 2011. Direct estimates for some districts are based on a very small ACS sample and hence have unacceptably high variance. I'm going to skip that. The model-based approach we adopted was to build a district-level regression model to predict this P, the probability of proportion that are LEP, based on variables in the ACS. Then classify districts into classes with similar predicted Ps based on the model. This is something I call predictive mean stratification, and it is intended to simplify the calculation and also to convey some robustness to misspecification of the model. Then within classes, apply a beta binomial model, which essentially shrinks the proportions towards the overall mean within that class. Then you compare the estimate from this beta binomial model with 5% to determine whether it qualifies or not. So the rationale is that this shrinkage from the beta binomial will give you more precise determinations for these small districts and then increase the chance of getting the thing right. One thing that's interesting about Bayes here actually is that for small districts and small proportions, posterior distribution is actually quite skewed to the right, as indicated in this diagram here. So how you actually choose the estimate here for the cutoff really matters. So the mode is different from the median, and the median is different from the mean. So what is the right choice of estimate here? The median, the mode, the mean? So Bayes actually forces a choice, and this could be based on a loss function. I actually like the posterior median for this problem. But it's interesting because the design-based or the superpopulation model approach assumes everything's symmetric. You have large samples. You have to worry about if this issue doesn't come up. You just use the maximum likelihood estimate. The maximum likelihood estimate is actually not a very good estimate for this. Posterior mode, which is sort of the equivalent here, is not really a good estimate for any particular reasonable loss function. So it's interesting that Bayes forces the issue there. The other application, the American Community Survey, the US Census Bureau makes thousands of ACS tables with millions of cells. A high fraction of these cell estimates are based on very little data. hence very noisy. The statistical problem is what the ACS provides is a direct estimate, design-based estimate, with a margin of error. And you're instructed to look at the estimate plus or minus the margin of error as the confidence interval. Actually, it's 90% at the Census Bureau. Well, this works okay in large samples, but for small samples, there are two problems. One is that the symmetric confidence interval is a horrible confidence interval, doesn't have the right coverage, and it can go beyond 0 and it can go beyond 1, which sort of bothers users to have something that's a proportion that goes beyond the value 1. So it's asymptotic. But in a small sample, the implied confidence intervals don't have the stated coverage. And so the goal here is to replace this by what I would call calibrated Bayes, which is replace the confidence interval by a posterior credibility interval from 5% to 95%, with the goal of trying to improve the nominal coverage. Actually, this is a table from a demographer who gave a talk at the Census Bureau when I was there. I just wanted to skip over it quickly, but this is for one particular area, St. Johns County in Florida, where you have the poverty rate and then the margin of error. And if you look at the ones which have the arrows here, the margins of error exceed the estimates. So if you calculate a confidence interval, then it goes negative, which bothers the users quite a bit. And actually bothers the National Academy panel that was looking at the ACS recently. So, well, you can try and do a full Bayesian hierarchical model for these proportions, and that's what I really like to do, but it's too much work. So a pragmatic pseudo-Bayesian approach that was actually suggested by Tom Lewis, who was my successor at the Bureau, compute design-based estimate and the standard error using standard design-based methods, then pretend the data are binomial with a number of successes x star and sample size n star that leads to the same estimates as in A. Then compute a beta posterior distribution with a non-informative prior. We're looking at uniform or Jeffreys here. And then just calculate a 90% posterior credibility interval based on this beta posterior. So this is very simple to do, and in simulations which I've been doing with folks at the Bureau who are listed here, we're working on this right now, it actually easily beats the standard wall-based confidence intervals in simulations, and it's a very simple thing to do. What are the barriers? Clearly I'm talking about a major paradigm shift here, but I think the conference is about paradigm shifts, so maybe it's a good place to throw it out there. People complain that it's too much work and computation, but you know, people do Bayes for all kinds of complicated things now, and it's a crock in my view. I mean, we can do such complicated computing these days. We have such power that I don't think it's really an issue. More explicit dependence on the choice of the model. Concerns with model misspecification, I think that's valid, but design-based methods are really not model-free in practice. They're making assumptions, but they're just buried in the background. I think models are essential for today's data, and I think calibrated Bayes is a great framework for it. So thank you very much.